Welcome back, space enthusiasts. Get ready to have your minds blown, because James Webb Space Telescope just broke the universe with an incredible new discovery. Prepare to embark on a journey beyond our wildest dreams as we unveil the jaw-dropping revelation that's rewriting the cosmos. Stay tuned as we dive into the extraordinary findings that are reshaping our understanding of the universe itself. Don't miss this mind-bending revelation. Hit that subscribe button and join us on this cosmic voyage. Let's boldly go where no one has gone before. If you want to know what the universe looks like, all you have to do is just look. The better your eyes, the better you'll see. When the James Webb Space Telescope first opened its eyes and peered into the deep universe, what it found was quite surprising. A multitude of young, massive galaxies that appeared far older than expected. Well, according to the conventional model of cosmology, accounting for dark matter, dark energy, normal matter, and radiation, these types of galaxies would require substantial amounts of time to form, grow, and evolve. With all of these galaxies found between 300 to 400 million years after the Big Bang, is modern cosmology, and by any means the Big Bang, in trouble? How might these findings reshape our cosmological understanding? Well, let's find out. On July 12, 2022, NASA released the first images from the James Webb Space Telescope. Within just a few weeks, scientists and astronomers all over the world were treated to high-resolution, full-color photos of galaxies, stars, nebulas, and planets. This is currently the deepest and sharpest infrared image of the distant universe. Although I do wonder how soon Webb will break this record again. Almost every single dot in this image is a galaxy, not a star, meaning each one contains millions or even billions of stars. The exceptions are the ones with sharp lines emanating out of them. Those ones are stars within our own galaxy that happen to be between us and the galaxies Webb imaged here. In the image, you will also notice that some of the galaxies, mainly around the center, seem to be stretched out into an arc shape. This is because they are near supermassive galaxies with so much gravity that their light is bent, causing what we call gravitational lensing. This isn't the first deep space view we've captured. Hubble, back in 1995, gave us the deep field image you see on your screen. When we compare them, Hubble's deep field covers a small portion of the sky, about 1/13 the size of the full moon, and reveals around 3,000 distant galaxies. You can easily notice how much clearer and more detailed Webb's view is. Going further, the telescope also took a picture of the Southern Ring Nebula, a type of nebula named for its resemblance to planets when viewed through early telescopes. Comparing it to Hubble, Webb's image is much clearer and more detailed, showing things that were hidden before. But here's the exciting part. Webb used a different camera to take a second picture of the nebula using a slightly different kind of light. Look at these two pictures side by side, one on the left in near-infrared and the other on the right in mid-infrared. Can you see something new in the right picture? Focus on the center of the nebula in the mid-infrared image. Scientists discovered something very intriguing. There are not one, but two stars at the heart of the Southern Ring Nebula, a binary or double star system. This is an exciting find that will provide valuable information for scientists in the future. And then we have the Stefan's Quintet, is a fascinating group of galaxies that show us how galaxies interact over millions of years. This new information helps scientists understand how galaxies collide and interact in a whole new way. While we call them a quintet, only the top four are really interacting with each other. The one in the bottom left, NGC 7320, is actually not close enough to interact with the others. It's much closer to us, just 40 million light-years away. The other four are about 290 million light-years away. In the grand scheme of the universe, they're still relatively close. You can especially see the effects of two galaxies merging, not just on each other, but on the other two galaxies as well. They seem to curve toward the merging galaxies. The top galaxy in the quintet also has a supermassive black hole at its center, which is actively pulling in material and emitting light energy equivalent to 40 billion suns. Next up, the Carina Nebula. The Carina Nebula is a vast star-forming region in our Milky Way, about 7,000 to 8,000 light-years away. It's huge, spanning about 300 light-years. It's a place where new stars are born, some of them extremely massive. James Webb focused on a specific area within the Carina Nebula called NGC 3324, known as the Cosmic Cliffs. It's a small region but packed with scientific discoveries. Comparing Hubble's view with James Webb's, you can see dramatic differences. On one side of the cliffs, there's a big cavity carved by young stars. They emit radiation and winds that evaporate surrounding matter. On the other side, in the gas-rich area, new stars are forming. What we see as blue steam is hot ionized gas blown out by young stars. Okay, so this last piece may not be a pretty picture like the others, but the data detected was amazing. The telescope performed a transmission spectrum of exoplanet WASP 96 bits as it passed in front of its star, analyzing the light that passed through the atmosphere of the exoplanet. Finding planets around distant stars is a challenging task because they are much smaller than the stars themselves. One way we detect these planets is when they pass in front of their parent star, as seen from our telescope. When this happens, the telescope's instruments notice a temporary decrease in the star's brightness caused by the planet blocking some of its light. To learn more about these planets, including their composition and atmosphere, we analyze the light from the planet that has passed in front of the star. By comparing this filtered light to the original unfiltered starlight, we gain valuable insights. Here is where the fun part starts. In 2011, the Hubble Space Telescope captured an image of one of the oldest galaxies called GN's 11, located 13.4 billion light-years away. This image showed us the universe as it looked 380 million years after the Big Bang. Up until the discovery of Jade's GN's 130 in 2022 by the James Webb Space Telescope, GN's 11 was the oldest and most distant known galaxy yet identified in the observable universe. But the problem now is these galaxies were relatively small compared to what James Webb discovered. Again, early in 2023, astronomers using the James Webb Space Telescope detected what appeared to be 6 massive ancient galaxies, which astronomers were calling universe breakers, because their existence could upend current theories of cosmology. The galaxies in question originated during a period when the universe was merely 3% of its present age. What's remarkable is that they exhibit sizes that far exceed what was conventionally believed possible for galaxies at such an early cosmic epoch. These objects are way more massive than anyone expected, said Joel Leisure, an assistant professor of astrophysics at Penn State University. We expected only to find tiny, young baby galaxies at this point in time, but we've discovered galaxies as mature as our own in what was previously understood to be the dawn of the universe. The observations came from the first data set released from the telescope. While sifting through images, Dr. Erica Nelson of the University of Colorado Boulder spotted a series of fuzzy dots that appeared unusually bright and unusually red. Redness in astronomy is a proxy for age because as light travels across the expanding universe, it is stretched out or redshifted. These galaxies appear to be roughly 13.5 billion years old, placing them about 500 million to 700 million years after the Big Bang. These would not be the oldest galaxies observed by James Webb. In 2022, scientists spotted 4 galaxies that date to about 350 million years after the Big Bang, but these were far smaller. Calculations suggest these 6 latest galaxies harbored tens to hundreds of billions of sun-sized stars worth of mass, putting them on par with the Milky Way. Explaining the existence of such massive galaxies close to the dawn of time would require scientists to revisit either some basic rules of cosmology or the understanding of how the first galaxies were seeded from small clouds of stars and dust. Existing models suggest that after a period of rapid expansion, the universe spent a few 100 million years cooling down enough for gas to coalesce and collapse into the first stars and galaxies began to form, a period known as the Dark Ages. The discovery of such massive galaxies so soon after the Big Bang suggests that the Dark Ages may not have been so dark after all, and that the universe may have been awash with star formation far earlier than we thought. For galaxies to form so fast at such a size, they would also need to be converting nearly 100% of their available gas into stars. We typically see a maximum of 10% of gas converted into stars. Boyd and Colchin said so, while 100% conversion of gas into stars is technically right at the edge of what is theoretically possible, it's really the case that this would require something to be very different from what we expect. If there are other faster ways to form galaxies than the current model allows, or if more matter actually was available for forming stars and galaxies in the early universe than was previously understood, astronomers would need to shift their prevailing thinking. The 6 galaxies' ages and masses are initial estimates and will need follow-up confirmation with spectroscopy, a method that splits the light into a spectrum and analyzes the brightness of different colors. Such analysis might suggest that central supermassive black holes, which could heat up the surrounding gas, may be making the galaxies brighter, so they appear more massive than they really are. Alternatively, the galaxies might actually be seen at a time much later than initially estimated due to dust that causes the color of the light from the galaxy to shift redder, giving the illusion of being more light years away and thus further back in time. Based on the current theory, it's supposed to take much longer for the appropriate shape to manifest. So how did these ancient galaxies manage to form spiral shapes with such efficiency? In an attempt to come up with an explanation, astronomers relied on a classic factor: dark matter. Scientists see invisible dark matter as the primary external force in the universe. While gravity pulls at objects, dark matter pushes on them to ensure they behave in a predictable manner. This is why, for instance, rapidly rotating galaxies aren't flinging stars and planets across the universe. In fact, NASA's most powerful supercomputers can't even come close to replicating our universe without using massive amounts of dark matter as glue. Is it possible that dark matter was more concentrated in the early days after the Big Bang, thus allowing galaxies to form disks earlier? The universe is indeed ever expanding from an initial explosion of hyper-concentrated matter and energy, which would seem to make sense. However, this does not account for dwarf galaxies, for instance. Astronomers have identified a total of 8 dwarf galaxies orbiting the Milky Way, which are essentially growing clusters of stars and matter that have not yet been swallowed up by our galaxy's gravitational pull. According to all the simulations using dark matter, this remains a complex and evolving area of study in cosmology. There should indeed be hundreds of these dwarf galaxies, but the discovery of only a handful raises intriguing questions. To make matters more complex, scientists have recently discovered clusters in the universe that contain virtually no dark matter. For instance, the Hubble Space Telescope provided images of a galaxy known as NGC 1052DF2, which contains so little dark matter that its density is low enough for astronomers to see through it. Meanwhile, Chinese astronomers found a dwarf galaxy, 94 million light-years away, called FAST G0139 plus 4328. This galaxy is the exact opposite, with 98% of it being concentrated dark matter. So if this strange, unprovable element really is the glue that holds the fabric of the universe together, why doesn't it exist in consistent amounts? Well, I'll leave it for you to answer in the comments. Carrying on those small lumpy blobs are light from an actual planet almost 10 times the size of Jupiter, and almost 400 light-years from Earth, known as HIP 65426b. It orbits a star much larger than our Sun and is very young. So young in fact that it's still warm from the primordial heat of its formation, glowing brightly in infrared light. Those infrared photons travel directly from another world to reach James Webb's magnificent mirror, creating the images. Astronomers using the Hubble Space Telescope conducted the first spectroscopic survey of Earth-sized planets in the habitable zone of the TRAPPIST-1 system. Hubble revealed that at least 3 of these planets do not seem to have puffy, hydrogen-rich atmospheres like gaseous planets, such as Neptune and Uranus. Instead, their atmospheres may be more shallow and rich in heavier gases, similar to Earth's atmosphere, containing carbon dioxide, methane, and oxygen. Sensing these minuscule modifications in a star's light is challenging from Earth's surface, due to atmospheric interference causing stars to appear blurry, which is why stars appear to twinkle. The Hubble Space Telescope's position above Earth's atmosphere, along with its ability to accurately point at objects for extended periods, allows it to detect subtle details in the light of distant stars. The James Webb Space Telescope was also used to measure the temperature of the rocky exoplanet TRAPPIST-1b. This measurement was based on the planet's thermal emission, detected in the form of infrared light. The result indicates that the planet's day side has a temperature of about 500 kelvins and suggests that it lacks a significant atmosphere. This achievement marks an important step in determining whether planets orbiting small active stars like TRAPPIST-1 can sustain atmospheres needed to support life and showcases the capabilities of Webb's mid-infrared instrument. Once again, NASA's James Webb Space Telescope has expanded our cosmic knowledge and continues to provide valuable insights into the universe's mysteries. This time, it made an intriguing discovery 120 light-years away in the Leo constellation. Researchers have named this distant exoplanet K218b. While its name may not stand out, its potential significance certainly does. This exoplanet, nearly 9 times the mass of Earth, falls into a category known as a high-C exoplanet. What makes it special is its potential to possess a hydrogen-rich atmosphere and a surface covered by a water ocean. NASA's observations of the planet's atmosphere hint at the possibility of an ocean world. They noted an abundance of methane and carbon dioxide, along with a shortage of ammonia. This chemical makeup supports the hypothesis that an ocean might exist beneath a hydrogen-rich atmosphere on the planet. However, what makes this finding even more remarkable is the potential presence of a molecule called dimethyl sulfide, DMS, which on Earth is produced by living organisms, particularly phytoplankton in marine environments. While the presence of DMS is still awaiting confirmation and further investigation, upcoming observations by the James Webb Space Telescope could provide clarity. This potential discovery of DMS on K218 is significant because it hints at the possibility of life, although it does not guarantee it. The exoplanet's location in the habitable zone, its relatively large size, and the presence of water make it an exciting subject of study. When the James Webb Telescope sent back stunning photos of the Rho Ophiuchi cloud complex, the images showed a complex of interstellar clouds, all with different nebulae, including dark nebulae. Though it's estimated to be 460 light-years away from Earth, it is still one of the closest star-forming regions to our solar system. Upon close inspection, astronomers were able to observe jets bursting out of young stars and various clouds of cosmic dust colliding into one another. According to prevailing theories, these clouds will eventually contract under their own gravity, forming a dense core called a protostar. As this protostar continues to contract and heat up, it will ignite via nuclear fusion. For scientists, the Rho Ophiuchi cloud complex was an almost unbelievable sight. However, as with so many other revelations brought forth by the James Webb's images, there were questions as well. For instance, astronomers still have a lot of questions about where the original stars in our universe came from and how they may have eventually transformed into the billions of black holes spread around various galaxies. Maybe stars were very different in the early days of the universe. Going back to black holes, they were initially predicted by Einstein in his theory of relativity, but were later confirmed through the observation of matter and light surrounding suspected black hole locations. This time it made an intriguing discovery 120 light-years away in the Leo constellation. The concept was simple enough. Black holes form when massive stars exhaust their nuclear fuel and undergo a catastrophic gravitational breakdown. The core of the star collapses under its own gravity, creating a boundary where the escape velocity exceeds the speed of light. Anything that crosses this boundary is trapped by the black hole's gravity and cannot pull away. The first provable black hole was Cygnus X1, but its discovery was quite literally dwarfed 10 years later when scientists observed the Sagittarius A, a supermassive black hole which sits near the center of our Milky Way galaxy. After much debate and calculation, it was eventually determined that Sagittarius A had a mass of over 4 million suns. This is far too large to have formed from a single dying star. The revelation quite literally sent astronomers back to the drawing board, where they were forced to reconsider existing knowledge on what they call galaxy evolution theory. Some began to suspect that black holes actually have the ability to join together, combining their relative mass over billions of years until they form these supermassive phenomena. But our concept of black holes and galaxy evolution theory would be changed yet again in 2021. That's when the James Webb Telescope helped prove that the supermassive Sagittarius A was actually, by black hole standards, quite small. J0 300 and 131806 is the most distant quasar ever recorded, and it's thought to be powered by a black hole with a mass of over 1.5 billion suns. But the problem with its existence is not only one of scale but of age. Indeed, theories about J0 300 and 131806 suggest it may have been formed after two spiral galaxies merged. The problem is that it's also estimated to be 13 billion years old. Given our current knowledge of the Big Bang, this means that this black hole would have had to accumulate this staggering amount of mass in just 600 and 800 million years. Though researchers have theories, none of them has proven satisfactory enough to earn the endorsement of the scientific community. And who knows, the James Webb could be waiting to prove any one of those theories wrong with a single image. The biggest question in the history of the world is where do we come from? And where philosophers and theologians generally take a human view on this query, astronomers want to know where the entire universe came from. Since the early 20th century, the prevailing theory on the creation of the universe revolves around the Big Bang. This started with Einstein's theory of relativity in 1915 and received a boost from Belgian astronomer Jwst when he proposed his ever-expanding universe theory. However, thanks in part to the James Webb Telescope, some scientists are now considering the fact that the universe might have evolved from nothing. The very first light ever emitted came from what's known today as the cosmic microwave background. It came into being around 380,000 years after the Big Bang and was caused by the very primordial hydrogen atoms that many scientists feel went on to create massive population 3 stars. In fact, this background may actually form a barrier that keeps us from seeing the actual origin of the universe. For the Big Bang theory to be correct, the universe would have had to be its subatomic size before the explosion. This was not simply a particle or even the particle, but every particle in existence pressed into a single unit. While theoretically possible, we cannot prove it via direct observation. Though there have always been doubters to the Big Bang theory, the James Webb's discovery of such perfectly organized galaxies from so early in the universe's history turned Big Bang dissension up to 11. Some scientists began to push back against the idea of a single origin point and instead suggested that the universe has no center. If there was a bang of any kind, it would have happened everywhere at once, meaning it was a completely spontaneous event. Other researchers began to question the ever-expanding universe theory, pointing out that while galaxies do move, they seem to drift away from each other rather than from some imaginary central point in space. Finally came the question of the universe's composition, which in theory should comprise both matter and antimatter in equal amounts. But antimatter is extremely rare in comparison to matter. How could this be possible if everything exploded from a single condensed ball of mass? The answers could push the boundaries of science fiction, let alone science. Perhaps the Big Bang was really just a collision between two universes, a regular universe and an anti-universe. In the former, some theorize time moves forward, while in the latter it moves backward. This concept is described as having the shape of an hourglass with both universes, stretching away from one another at the point of their collision. This theory partially drew on a discovery in 2004, when we got our first thermal replica of the cosmic microwave background. As this is the remnant of the radiation emitted after the supposed Big Bang, it should be more or less the same across all its parts. However, scientists quickly learned this was not the case. The center axis boasts a huge stretch of above-average temperature. There are also cold and hot spots breaking up the uniformity. One cold spot in particular is very large and has been shown to emit strange radio waves. Could this be the point where our universe intersects another? Some scientists, including the late Stephen Hawking, say it's very possible. Though the Big Bang theory is still the prevailing concept for how our universe began, the James Webb Telescope is forcing scientists to alter how they understand and interpret that theory. Perhaps most impressive of all is that we are only at the beginning of the telescope's planned 5.5-year primary mission. In total, the James Webb Space Telescope could continue to define and redefine our understanding of the universe for the next 2 decades. And that's pretty much it. Whenever you dare to ask the universe what is true, you'd better be prepared to listen to what it tells you. Thanks for watching, and I'll see you in the next one.